Welcome to our 10th video. It's very apt to start with David Bowie and Starman because we're going to be considering real-world applications of vectors to a space rendezvous. I asked you to watch the trailer for Gravity. There were one or two moments where it was essential that two objects or two humans had to be in the same place at the same time. You can see in this little image, Sandra Bullock is desperately trying to have her hand rendezvous with this bit of the spacecraft. To be there at the same position at the same time is essential to her survival. Before we do that, we have to think of the idea of a velocity vector, which we can see here. So we've got a blue vector and a red vector. They each represent velocities, and they can do this because the parameter multiplying them, which sometimes we've called lambda or mu, some real number. In this application, it's time. So we have a particle positioned at the origin, and its position is determined by a scalar multiple of the velocity vector, but the scalar multiple is time. So the question is, which particle is moving fastest? You can see the speeds are pretty similar, but in fact the red particle is moving fastest simply because the magnitude of the red velocity vector is the square root of 9, and that's greater than the square root of 8. So every unit of time it travels further, and that's what we mean by going faster. It's easy to have two vectors which are completely different. They go in different directions, but they amount to the same speed. That's important. That shows how different speed and velocity are when we consider vectors. Okay, so everything we're doing today, the direction of a particle is also its velocity. So it's easy to figure out that if we have a velocity vector, its speed is the magnitude of the vector, and that's the same in 3 dimensions. You can even use unit vectors to find the velocity of, the velocity vector that gives any required speed, k. You simply make the unit vector by dividing by the magnitude of the vector. That would then have speed 1 units per second, and then multiply it by k to make it have speed k meters per second. So we're going to solve a real-world problem. You are going to develop a model, test the model using GeoGebra. If it works, there are extensions to make, which I expect some of you will do. If it doesn't work, then you have to think again about your model. Here's the situation, and we will test this on GeoGebra in a moment. So there's a space station at this coordinate called P, and a space station at this coordinate called Q. Space station P sends out an astronaut on this velocity vector at time is 0. Space station Q sends out an astronaut to rendezvous with P's astronaut, but sends out the astronaut called AQ. A minutes later, So that's crucial. This astronaut does not leave at the very moment that P's astronaut leaves. It's a delay of A minutes, and it has this velocity. Now the problem is, what is the value of the delay to make the astronauts meet, to make them rendezvous at the same position, the same time? And we can use this GeoGebra file I'm going to show you to check our answers. The astronauts will turn green if they successfully make a rendezvous. So here's how it works. At the moment the delay is 1 second. If I press start, you'll see the astronauts start to move. You can see they came close to each other, but they did not rendezvous, and that, in this context, is a disaster. And this is a delay of 1 second. So the point of the problem is to calculate what that delay must be. You might be tempted to do it by trial and error, but of course that's kind of cheating, isn't it? You can work it out using vector methods. So I'm going to leave you to think about that. Like I said, it is problem solving, really. This is a problem solving process. And when you've figured it out, there are other extension questions which I'll send you. I've solved the ones in the red boxes. They're quite good fun to solve, and they'll really stretch your imagination. When you've done that, you will have been acting as good IB students. Vector theory can be used for other purposes, such as coordinating when a cargo ship is refueled at sea, or coordinating search and rescue missions at sea, as well as for harmful purposes. It's interesting. We all remember that Einstein was horrified when he realized the power of his discoveries with splitting the atom. And maths can be applied in peaceful, beneficial ways. Then you'll be ready for your final homework, which I will send to you.